In this video, we're going to discuss the integrated rate laws. Since the rates change with time for most orders of reaction, it's hard to use a rate and determine how much of something will be left because that rate's going to alter as things are consumed. If you tried to use the average rate determined from the beginning and the end point, your actual calculation would be wrong at every time in between. That's not a particularly useful value then. So how do we find the actual amounts of a chemical if the rate is constantly changing? Well, the shorter your change in time, the less change in rate there will be from the start to the end. If you can bring your difference in time down to infinitesimally small, then your rate should be effectively the same at the start and the end, and your calculation would be accurate. The idea of calculus, integration. Using this, we can actually create a formula that lets us calculate out the accurate concentration at any time. It will change depending on the order. And so we have a first order integrated rate law, which says that the natural log of the concentration of your material at its beginning divided by the concentration of material at time is equal to the constant times the time. Using the natural log of that difference, we're able to account for the continuous change in the rate over time. First order reactions like this are first order overall. So this is something like radioactive decay or one material breaking apart into other things. This has a first order reaction and it's first order in A. And so our rate would equal K times the concentration of A. For this type of reaction, especially things like radioactive decay or molecular decays, we often talk about the half-life, which we can actually find from this equation. The half-life is how long for half the material to go away. Well, if we think about that equation, natural log of whatever our starting amount was, we'll just declare it 1. I want half of that. Doesn't matter what the top actually is. If you have half as much on bottom, this comes out the ln of 2 when you do the division. That must equal K times the time, which for the half-life is T1 half. So the time for half of a material to radioactively decay is equal to 0.693, the natural log of 2, divided by the rate constant. This is often a more handy value than the rate constant itself. If someone wanted to know how long it took for radioactive material to decay away, knowing that half of it is gone in a certain amount of time, it's much easier than being told a constant and having to calculate out how much time. And so often we report things as T1 halves. Let's go ahead and use this to calculate out a constant using the half-life. For something like uranium-235, whose T1 half is 7 times 10 to the 8 years. So 700 million years is the half-life. Well, in this case, we can solve for K by rearranging. Natural log of 2 divided by the half-life should equal our K. So 0.693 divided by 7 times 10 to the 8 years. Making our K equal to about 9.9 times 10 to the minus 10 per year. Well, we can normally solve K through various rate data from various runs. We also can solve it if we know the half-life and use the integrated rate law. Well, if there's a first order rate law, why we need to specify it? Because there's also a second order rate law. This would be for a rate where it was equal to K times 1 chemical squared. So this is two of the same material interacting with itself. There may be other chemicals in the reaction, but the rate law is just 1 chemical to the second power. In this case, what we end up with is 1 over the concentration at time minus 1 over the initial concentration must be equal to KT. This also has its own half-life concentration, which is 1 over the constant times the initial concentration. For a second order system, the half-life is actually dependent on the initial concentration of the chemical. The more of it there is, the faster it reacts to the second power. And so doubling your initial concentration will give you 4 times your rate. That means you will be decreasing more quickly from a larger concentration. So the half-life is dependent on that initial concentration. There's also a 0th order rate law, which is independent of the concentrations. This is just your rate is equal to a constant. If we wanted the half-life for such a situation, this is going to be equal to the original concentration divided by 2K. It goes away so quickly, depending on how much stuff you have, it takes a certain amount of time for half of that to go away. Since the rate is just dependent on K, the half-life is dependent on the initial concentration of A and how long it takes for K to get to half of that. When you're doing a reaction, how do you know which of these applies, however? As stated before, we don't know the orders of a reaction until we experimentally determine them. This is one way that we can. For a first order reaction, if you set your equation data up so that the ln of your concentration at time is equal to negative kT plus the ln of your initial concentration, well, y equals mx plus b, you make a plot of this. So you would take your actual time data and your actual concentration at time data, you'd take your natural logs, and you'd plug them in and plot your natural log of concentration at time versus time. And what you'll find is you should get a negative slope. We have negative k. Our slope is going to be equal to our negative k. Our intercept will be our natural log of our initial concentration. If the reaction that you performed was first order, when you plug in this data, you should get this line. If you don't, if your real data curves off or does something else, then it's not first order. If, however, it does create a negative sloped line like this, then your data was first order. And so this is a handy way to be able to check real quick. Additionally, if we want to check to see if it's second order, well, you need the 1 over concentration at time to equal kT plus 1 over initial concentration. Again, mx plus b, but this time your graph, you're going to plot 1 over your concentration at time versus time. And so you check and see how much your material's concentration has changed at various time units, and when you plot this, you should get a positive slope. Slope will again be equal to k, but positive this time, as that was how the equation works out. Our intercept will be 1 over the starting concentration, and if your data is second order, you will make a straight line with a positive slope. If your data was something else, then when you plot these forms of your data, you'll get a line that curves off some direction. It won't fit appropriately. And additionally, if it's 0th order, if first and second didn't work, then you can plot the concentration at time is equal to negative kT plus the initial concentration. And this should give us a graph that when we compare the concentration at time versus time, should show it decreasing. Now, at first glance, this might look like the one up above, but remember what we're plotting. Natural log versus just the raw concentration. Your concentration in a 0th order changes the same amount for the same amount of time no matter what. It's not dependent on concentrations. However, if you tried to plot a first order reaction here, it would curve off as it changes over time. And so by plugging in the data you actually obtain into these 3 different forms, you can see which one fits to know whether your reaction was a first, a second, or a 0th order reaction. So here's another way that we can use the data to calculate out order. Effectively, this is doing what we did before, comparing different points, but it's comparing all of our points at once in a graph and letting us see which one it fits.